Okay. So, I guess today we'll do what's on the homework. It's a beautiful day, so try and be quick. I think a lot of people are doing better things with their time now. But, okay. So, let's start with problem 26. Okay, so we have a train station to which customers arrive in accordance to the Poisson process having rate lambda. So a train is summoned whenever there are n customers waiting in the station, but it takes k units of time for the train to arrive at the station. So we have so okay, and when it arrives, it picks up all the waiting customers. And now, assuming that the train station incurs a cost at a rate of nc per unit time, whenever there are n customers present, find the long-run average cost. So, the station incurs cost at rate nc per unit time when n people are present. And we want to find the long-run average cost. So this is a pretty classic renewal reward problem. So let's first sort of break this process up into cycles. So let's say a cycle corresponds to successive departure of or arrivals of the train, or departure. Successive arrivals of train. Okay, and then we know that that's a renewal process, right? So now, the long-run average cost would be the expected cost per cycle divided by the expected length of the cycle. And that's just by basic renewal reward theory. So let's do first, and let's say this is EC and this is EL. So let's first calculate the expected length of a cycle. So that's pretty easy because first of all we want n people to have arrived, and after they have arrived we also have to wait an additional k time units. So the expected length of the cycle will be n times the expected time it takes for one customer to arrive, which we know because it's a Poisson process, it's just 1 over lambda. And then we have to add on this additional sort of time k. So that's pretty simple. Now, okay. So now to calculate the expected cost during the cycle, we sort of need to break it down into two things. Because we have the cost that's incurred when, no people are there, one person is there, two people are there, so on and so forth, until n minus 1 people are there. And then we have the cost after the nth person has arrived, which corresponds to that, and where we don't really know how many people will have arrived in this time interval k. But it's not very hard to figure it out. So, okay. So this sort of corresponds to the average time which no one's in the station. Now we have one person. Now we have two. So on and so forth until the n minus first person. Okay. And then, I'll explain this. We have this term here. And why is that the case? Well, okay, so after arrives, expected number customers at the station is, of course, n, because we know that we at least have n. But now, because people still are arriving according to this Poisson process, we know that we will also have an expected number of people, lambda t, where now t can only range from 0 to k. Because we have this time interval, and we know that at any point within this interval, the expected number of people that are present is lambda t. So now to get the cost that will be incurred in this time interval, we just have to integrate from 0 to k n plus lambda t dt. Because we know that no matter what, we'll only wait for k time units. So expected number of people is going to reflect that. And this ends up being nk plus lambda k squared over 2. So this is sort of the logic of what we're doing. And now we just take the ratio of the two. So, and I guess we have a nice little expression there for it. Okay. So, and note that this is a nice result because, for a very practical reason, say that we want to minimize the long run average cost, and we have freedom as to what this k variable can be. We can choose k to be anything. So then, by just using some simple calculus, taking the derivative and blah blah blah, we can find the value of k which minimizes this. So it's not in the problem, but just as a side note. So any questions? Okay then. So let's now move on. Let's do problem 38. Okay. So here we have truck driver drives round trips from A to B and then back to A. So we have, city A, city B. Each time he drives from A to B, so the speed here, he drives at a speed that is uniformly distributed between 40 and 60 miles per hour. And when he drives from B to A, he drives at a fixed speed where S is equal either to 40 or 60 miles an hour with probability 1/2. And now we're asking a few questions. Okay, so the first question is, what long-run proportion of time does the driver spend driving from, is that the question? Driving from city A to city B. So first of all, let's consider, a trip, A, B, and then back to A, to be a renewal. Or a renewal cycle. So again, we will apply the renewal reward theorem. And now say that a reward of 1 is earned whenever we are traveling from A to B. Then we know that the long-run proportion of time, then by renewal reward theorem, we have the following. That sort of long-run proportion of time spent driving. How do we write this? So probability going from A to B in the long run is just the expected time we spend going from A to B during a typical cycle, divided by the length of the cycle, which would just be the sum of the two expected times. Okay. So now it's a relatively easy thing to calculate these expectations, because now in the first case, or I guess what we know is that our speed is random. So we just need to condition on what our speed is in order to find how much time it will take us to go from point A to point B. So going from A to B, we know that our speed is uniformly distributed between 40 and 60. So we just write this integral, and then we remember the formula that space is equal to time times speed. And so this will just be, oh, forgot to mention that, we're saying there is a fixed distance here of d. So, the distance here is d. It doesn't matter what it is. So this would be d over s times 1 over 20 ds. So this becomes 1 over 20 times d times the log of 60 minus the log of 40, which is just equal to d over 20 times log of 3 over 2. So we calculated expected time it takes us to go from A to B. Now let's do the same from B to A, which is a little simpler because now there are only two options for what the speed can be. So our traveling time will be either d over 40 with probability 1/2 or d over 60 with probability 1/2. So this gives us a result of d over 48. So long run, or probability, let's say that this is p. So p is equal to d over 20 times ln 3/2 over d over 20 plus ln 3, no, times ln 3/2 plus d over 48. So all the d's cancel, and we're left with, yeah, whatever that ratio is. So any questions on this? Okay, so let's do part B then. So part B, we're asking in the long run, for what proportion of his driving time is he driving at a speed of 40 miles an hour? So now it's sort of a similar setup, but now imagine that, say that a reward of 1 is earned whenever he's driving at 40 miles per hour. So now again, the probability that driving at 40 miles per hour in the long run will again sort of be the expected reward, per cycle divided by the length of the cycle. But now this time, the expected reward will be, well, we know that he can only be driving at exactly 40 miles an hour if he's driving from city B to city A. And given that he is driving from city B to city A, he will drive at 40 miles per hour with a probability of 1/2. So the reward will just be, the expected reward per cycle will be 1/2 times 40. And the length of the cycle, of course, remains the same. So divided by. Oh, wait. Yeah, I forgot a D here. Yeah. So anyway, all the d's cancel, and we're left with this. No, wait, I'm screwing up. Going too fast. What am I doing? Okay. So, so the reward, so we have a reward of 1 whenever we're driving at 40 miles per hour. So we're driving at 40 miles per hour with probability 1/2. And how long will we be driving at 40 miles per hour? Well, it will be whatever the distance between the two cities is, divided by our speed, which we take to be 40. So, sorry about that. And then this cancels out. Well, actually, so any questions? Yeah, the denominator stays unchanged because the length of the cycle is the same, and we're considering again the same cycles. So we're just now taking the reward to be something different, so because we're calculating a different probability. Okay. So now let's move on. Okay. Let's do problem 41. So basically, what is problem 41 doing? It's concerned with the long run sort of average, the long run age and excess of a renewal process. So first of all, this is sort of just as an introduction. Is equal to this equilibrium distribution, which is equal to this guy here. So we have a renewal process, and say that we're observing it in steady state, or in where time is infinity, and we just pick a random time t, and we know that we'll have another renewal sort of a little later and one before it, and we're interested in getting the limiting distribution of the age and excess at time t. I'm assuming everyone, Professor Witt did this in class, like age and excess of a renewal process? No? Well, the age at time t is just basically, as the picture suggests, the time that has elapsed until, or from the time of the last renewal until time t. So if this is Sn of t, this is Sn of t plus 1. And then the excess at time t is just the time that's remaining until the next renewal after time t. Okay. So now, just so that this formula isn't mysterious to you, let's derive this. I mean, it's not very hard. So we take just the renewal interval, and we say that we earn a reward of 1 whenever the excess is less than x. Okay? Then by the renewal reward theorem, probability that at the limit our excess is less than x will just be, the expected reward during this cycle divided by the length of the cycle, or the expected length of the cycle, which we know is just mu. It's the mu. So now, what is the expected reward? Well, it's the expectation of this random variable here. And why is that the case? Well, because this is the inter-arrival time, right? Now, when is the excess less than x? Well, it can only be less than x when so we have a renewal here. Say that this is x. Let's say that the next renewal happens here. So when is the excess less than x? It's less than x in two ways. Well, it can either be less than x if the inter-arrival time itself is less than x, right? Because then the time to the next arrival is obviously less than x. And of course, if the inter-arrival time exceeds x, then the excess will be, of course, greater than x. So we're interested in this in the random variable of the minimum of x and x, because we want there to be less than little x time units until the next arrival. So now we do the tail integral formula. So if we say that this has distribution g, we know by the tail integral formula because it's a non-negative random variable. So we get something like this. Okay, and now let's see. Let's break this up into two parts, from 0 to x, and then from x to infinity. Now, when y is, so in other words, when the value of this random variable is greater than x, can the minimum of that random variable in x be greater than y? No way, right? The minimum is always x then. So this just becomes 0. This is 0. And then here, Well, what is the probability that the minimum of big X and little x is greater than y when big X is less than little x? It's just the probability that x is greater than y. So this is f bar y dy. Is this clear? You just need to remember the tail integral formula here. So, oops. So this is how we get the equilibrium distribution, which is the long-run distribution of the excess and the age. And a similar argument works for the age, too. Okay. So yes, well, let's actually change this to age of t, because no. I think that's right. Yeah, that's right. Okay. So now let's do the problem. So for part A, fe of 1 is the integral from 0 to 1 of, f bar x divided by mu. And now in this case, f bar x, f is uniform 0, 2. So it would be 1 minus x over 2 divided by the mean, which is just 1, dx. So this is the integral from 0, 1 of 2 minus x over 2 dx, which is 3 over 4. And now, what is the second case? So we have exponentially distributed with mean 1. So again, we do the same thing. And now this is just e to the minus x dx divided by 1. So this is just 1 minus e to the minus 1. So any questions? It's pretty straightforward. Okay, then let's do the next problem. Okay. Now, okay, the equilibrium distribution is defined. Show that if f is exponential, then the equilibrium distribution is the same as the regular distribution. So, let's see. So we have, let's assume, actually, okay, so lambda times e to the minus, oops, e to the minus lambda y dy divided by 1 over lambda. And now, of course, if we do this integral, so we multiply and divide by lambda, and what is this? This is just f of y, right? So f of x. Because, of course, here we're just integrating the density of an exponential from 0 to x. So we get the probability that that random variable is less than or equal to x. And note that this isn't surprising at all, right? Because what is this? This can also be interpreted as the distribution of the age in excess in the long run, right? But now it's like we have a Poisson process. And what do we know about the Poisson process? The interarrival times are memoryless, right? So no matter how far in the future you look, and also the process is stationary. So no matter how far into the future you look, the probability that you have an arrival within x time units will be the same as probability that you have an arrival in x time units at any other point in time, too. So this stands to reason. Now assume, I guess, random variable x is actually equal to some constant. So we have deterministic interarrival times. So I guess here x is exponential some rate lambda. Then fe of x just becomes, so when x is between, so when little x, actually let's write this. So fx is equal to 1 if x is less than or equal to c, and 0 if x is greater than c, right? So what do we have here? We no. F bar of x. Because if x is less than or equal to c, then of course the probability that a random variable is greater than x is 1. Because, well, c is greater than x. And then it becomes 0. So we end up integrating 1 from 0 to c. And of course the mean value is just c. So from 0 to x. So we get x over c. So in other words, the distribution here is uniform from 0 to c. Okay. Now let's do part C. So in part C, okay. So we're basically saying that meter maids come, parking officials. Is that offensive? Meter maids? I hope not. Okay. So when an official encounters a car, he or she marks it with chalk. If the same car is on the official's return 2 hours later, then a parking ticket is written. If you park your car in Berkeley and return after 3 hours, what is the probability that you have received a ticket? Okay. So here, the inter-arrival times are just identically equal to 2 hours. Okay. So now, the trick here is to understand that you will receive a ticket only if the parking official arrives in sometime in the next hour that you have parked. That's bad. In the next hour since. Okay. Within 1 hour after you parked. Because only then, he will arrive, he or she will arrive, and then they'll arrive again after 2 hours, and you'll get the second ticket, and you'll get a fine. So what we're interested in is the probability of this, the official arriving before within 1 hour. So, and I guess we're taking all of this to be in the long run. So that's why we take the equilibrium distribution, and so we decided that this is just from 0 to 1 dx, and now c is equal to 2. So the probability that you get a ticket is exactly 1 over 2. Or you could also immediately say that it's uniform on 0, 2, and substitute 1 here and 2 here. Okay. And now finally, let's talk a little bit about the inspection paradox. Okay, so inspection paradox has to do with sort of the age and excess of a renewal process. And basically what it's saying is that, actually, and all of this is xn of t plus 1. So what it's saying is that the probability that xn of t plus 1 is greater than some value x is always greater than or equal to the probability that x is greater than that number. So for all x. Which is sort of a paradox, right? Because you sort of think of this as just another interarrival time. But there's something special about it. Because now we sort of have more information, right? Because we know that nothing has arrived, basically, throughout this whole interval. So we already have some information that, well, this is probably a bigger interarrival time than usual. So, but we can show this pretty easily by conditioning on what the last arrival time before t is. So let's see. So the probability that xn of t plus 1 is greater than x, given that Sn of t is equal to, how do we condition here? Say t minus s. So let's say that this is time t minus s. So now, let's see. What is this if x is less than or equal to s? Can anyone tell me? Well, we know that the last arrival was at time t minus s. And then at time t, nothing has arrived. So that interarrival time necessarily, the probability that it's greater than x is, well, it's 1, right? Because we already know that it's greater than s, and s is greater than x. So this is just 1. Now, let's do something else. What is it? Now let's consider the case where x is greater than s. Okay. Well, what do we know? Well, we know that our interarrival time is already greater than s. So we basically want the probability that our interarrival time will be greater than some value x, given that it's already greater than some smaller value, little less. So now we can expand this. So we can write this as probability that x is greater than x and x is greater than s divided by the probability that x is greater than s. So, well, what is this probability here? Well, x is greater than s, right? So this probability just becomes probability that x is greater than x, right? Because if x is greater than x, if big X is greater than little x, then it's definitely greater than little s. So we get these two things. So okay. So now let's bring everything together and find out what this probability is. So now we've conditioned, so now we uncondition. And I guess Sn of t can be anywhere from 0 to t. So this will be probability actually so S ranges from from 0 to t here, and times whatever the probability that Sn of t is equal to t minus s is. Okay? Now, this probability, no matter what, let's also say this is also greater than fs, right? So this guy here is always greater than f of s, right? So f of s given Sn of t is whatever. Actually. So, well, so from that we can, no, f of x, I'm sorry. Okay, so then we can just take this out. And of course, whatever's inside here will integrate to 1. So that's how we get. I mean, this is just, it's not really necessary to do this, because I think it's very intuitive why the one probability is greater than the other, but this is just the mathematical way of verifying it. So, so now given this, I think that this problem is, I don't think I can do a better job of explaining it than what's in the solution. It basically says that it matters where you sample during the renewal. So, so they attempted to determine the average amount of time that tourists spend in the country, and they sampled 2 different ways. One way, they questioned randomly chosen tourists as they were leaving the country. And the other, they questioned guests who were in hotels. So, of course, they got different numbers for, significantly different numbers for people who were leaving versus people who were staying at the hotels. And, well, a very good explanation for that is that the people who stay at the hotels, since they're staying in a hotel, will probably stay for longer than the people who are, you know, on their way out and they're backpacking, or they, you know, where it's like a completely random sample. Whereas people who are in hotels, I mean, would, on average, probably stay longer. So, yeah. So that's about it. Any questions? Okay, thank you.